what we did last week was here we did the first law of thermodynamics, we did the Stefan-Boltzmann equation, varying how much sunlight came in with latitude and longitude, day-night cycle, and we had a single layer atmosphere. This is what I'd like to do this week. I've already implemented the sun going the right direction and a couple of other little bits. I want to add a color bar so that we know what values we're exactly looking at. We might just skip heat diffusion, to be fair. It's a pretty small effect. I want to introduce an equation of state for the atmosphere. An equation of state is basically an exchange rate between atmospheric parameters. Half of programming, for those of you who don't program, half of programming is Googling. I just want it to be known. Stack Overflow, every programmer's best friend. So let's try this. Aha! Now that's interesting. We had a little happy little blow up there. Wow, that's strobing though. That does not look good, does it? So obviously the color bar's in the wrong place. Ooh, now what's going on there? Okay, so to be honest, when you're spinning up a model, that's the term for when you started out from like completely fresh, you do see weird behavior like that. You'll see numerical weirdness because you're fundamentally taking continuous equations and quantizing them, and it makes them do weird shit. What's wrong here? Yeah, so we just need to make the figure a little bit bigger. I think that was it, wasn't it? Subplots adjust. Yeah, PLT, subplots adjust. And then I think we just want to go like left equals 0.1. Something like that. Nope. Okay. Again, this is also what half of programming is like, guys. So where does this start? It starts at 0.85, so let's finish the subplots at 0.8. This is how far across they are. There we go. Cool. Okay, cool. So now we have a color bar, and man, atmospheric temperature is going... That doesn't look good, does it? So why I think that's happening is just with the atmosphere is I think that's just a consequence of numerical shit that's going on. What you'll notice that it's like a what's the word I'm looking for here? An evanescence behavior, in that it only cools when it's sober, and as the ground temperature warms, the behavior kind of settles down to something a bit more normal. But this is effectively like it J-curving around the right solution. But because it's in finite time, it's doing that basically. I'm gonna skip over heat diffusion because that's something that we can do in the future. I want to focus on these three. That's the next kind of this is where shit gets really cool, in my opinion. So we need to talk about the concept of an equation of state. So as I said at the start of the stream, an equation of state relates one or multiple variables in a dynamical system to another. The most common equation of state that you'll find in the atmosphere, and there's a different equation of state for the ocean, is the ideal gas equation. So this basically, in normal form, the equation of state that you would see in school is PV equals nRT. So the pressure in a gas multiplied by the volume that gas occupies is equal to the number of moles in that gas multiplied by the gas constant multiplied by T. If you take V and put it underneath R, like this, what you can basically do is bind up and set that this volume is 1, so that the volume that you're considering is only 1 meter cubed. Then what you can do is add in the molar mass and divide the ideal gas constant by the mass per mole, and T here in the end. This then becomes the density, and then we call this term the specific gas constant. The version of the equation of state that you normally see atmospheric scientists use for the atmosphere is that the pressure at a point in the atmosphere is equal to the density of the gas that you have there multiplied by the specific gas constant multiplied by T. What that is basically telling you is that if you have, let's say that you have a gas of a given density, and you increase the temperature, then by doing that, you're going to increase the pressure. And likewise, if you decrease the temperature, you're going to decrease the pressure. Or if you hold a gas at a constant temperature, but increase the density, obviously the pressure is going to go up. That just sort of makes sense. The more gas that you have in a certain location, the higher the force it's going to exert due to gravity, the higher the pressure it's going to cause. But those two are competing factors against one another. So if we know what the temperature field is, and we know what the density field is, then you know what the pressure field is, right? And the pressure field is important because pressure dictates where air moves. So once you know what the pressure is, you can work out how the air is going to start moving. There are various approximations you can put into that. There are various assumptions that you can go about. So we know the temperature field, right? We have the temperature field here, the temperature of the atmosphere. Obviously, the planet's not going to flow. It's not a liquid, but the atmosphere can. But we don't know what the density is. The first approximation that you can do is that the gas is incompressible. The gas is at a constant density. Obviously, that is not a realistic approximation of the atmosphere. It's a half-decent approximation in the ocean. Water is fairly incompressible, but not quite. Whereas the atmosphere does tend to squidge. You actually do get areas with high and low density. For example, very cold areas will have higher density air. Areas that are, the equator, warmer areas are going to have lower density. We already have the temperature here. So let's create a new field. Let's just call it air pressure. And it's going to be exactly the same as our temperature fields. So it's over the same grid, over the same number of latitude and longitude points. And then what we can do really simply is take every time that we have air pressure equals temperature well, let's do it in the same order that you see it in the equation, shall we? So air density multiplied by specific gas. Normally I would literally just write this as R, but because Captain's watching, I won't. Specific gas multiplied by temperature. So it's taking this array, this matrix, and multiplying it by air density and specific gas. So we have our list of physical constants here. A reasonable approximation of air density is 1.3 kilograms per cubic meter. What we are doing is treating the atmosphere as a single slab, but obviously that's a terrible approximation, and so that's not an appropriate density for the entire atmosphere. But hey-ho. And we also need the gas constant, specific gas. So you may remember this as 8.315, is it? 8.314. Nearly there. It's not that, because remember, this is specific to, if you look at our derivation, it's basically that divided by the mole of mass of whatever substance you're considering. So it's going to be different depending on whatever gas you're considering. In atmospheric physics, it's obviously is going to vary depending on what mix of gases are in the atmosphere, but considering that it's 99% nitrogen and oxygen, it varies very little. You can basically model it as just being constant. Obviously that's an approximation, but a pretty good one. It's 287 for dry air. We're not doing moisture, okay? Speaking from experience, I'm just going to say this directly to the camera. We don't want to get moist just yet. Moisture adds so many complications. We're going to have a dry atmosphere, okay? Stay dry. 287.05, beg your pardon. Well, let's say it's 287, because we're already making a whole buttload of approximations. Let's just see if that's broken anything. Nope, we all look good. That's not a terribly interesting field to plot, because if you look at it, it's literally just a one-to-one correspondence with temperature, because we assume the constant density. What we're going to do instead is get the atmosphere moving.